Alrighty, good morning everybody, and welcome back to Abstract Algebra. Plan for today, we're going to talk about one of my favorite theorems of the semester, and definitely my theorem of the semester with my favorite name, SCAD, Fundamental Theorem of Finite Abelian Groups. As far as office hours go, I've got my usual ones, today and Wednesday, the hour before class is from 2 to 3. Tomorrow morning from 10 to 11:30, tomorrow afternoon from 1:30 to 2:30. And as far as homework goes, lest we forget, homework 5 will be due on Wednesday. Where homework 5 has questions on it regarding isomorphisms/homomorphisms, as well as a few questions about cosets and Lagrange theorem. Does anybody have any questions or comments before I get started for today? So just a heads up, I will be assigning a new homework set either Wednesday or Friday, depending on when I get to it. And it's going to be about a card game. So it's going to be a fun one. Alrighty. So last time we were talking about, I had given you the fundamental theorem of finite abelian groups, but we hadn't really had a chance to work out an example of it quite yet. So this theorem basically tells you, given any number n, how can you classify every abelian group of that order? So what it says is, let G be a finite abelian group, and then for some primes P1 through Pn and some powers R sub I, satisfying the order of G is the product of these primes to these powers, or notice that these P sub I, these primes, could repeat themselves, potentially. If G is a finite abelian group with the order of G that can be written out in this way, it has to be the case that there is some way of saying that G is isomorphic to the direct product of a bunch of copies of Z mod these powers of primes. And moreover, this decomposition of G must be unique as such, meaning given any finite abelian group G, there's exactly one way to write it as the direct product of a bunch of copies of Z mod P to some power Z. Yeah, Elaine?
Could we maybe have a joke?
Oh my gosh, forgot to do a joke of the day. Oh my gosh, I don't have a joke of the day. Elaine, give us a joke.
No, I don't have my book with me.
Elaine, give us a joke.
I cannot.
Most disappointing.
Please.
All right, fine. I'll steal one of Dr. Gabler's. What's purple and commutes?
This
It's an abelian grape. So, yeah, sorry about that. We forgot to do a joke. I blame the fact that this is the only class I'm teaching today because my other classes all have exams. So let's look at this example. We're going to classify all groups, all abelian groups, of order 675. And when I say classify all abelian groups of order 675, what I mean is I want to come up with a list of groups and basically say any abelian group of order 675 with that many elements in it has to be isomorphic to one of these things in this list. And our strategy, starting off, is just going to be to see how can we find a prime decomposition of 675? And what y'all came up with last time is that 675 is going to be equal to 3 cubed times 5 squared. 27 times 25, in other words. So this is going to be our way of breaking up 675 into the product of primes. 3 times 3 times 3 times 5 times 5. And for each one of these, we're going to write down how many ways are there to write 3 cubed and 5 squared as the products. In other words, how many ways can we factorize just 3 cubed and 5 squared individually? And what we found is we could just write 3 cubed as 3 cubed by itself. We could write it as 3 squared times 3, Or we could write it as 3 times 3 times 3. And 5 squared we could just write out as 5 squared or 5 times 5. For kind of the ways which we could split up and factor 3 cubed as just in terms of powers of 3. Just 3 cubed by itself, a 3 squared times 3, or 3 times 3 times 3 individually. And 5 squared we could similarly get 5 squared or just 5 times 5. And check this out. You make a little table here, where for each way to write 675 now as a product of primes to some power is going, each way of factorizing 675 using these methods of factorizing 3 cubed and 5 squared is going to give us a different group of order, a different abelian group of order 675. So here's going to be our factorizations. One is just going to be 3 cubed times 5. This is going to be as a 3 cubed times 5 squared. Kind of have as big powers of 3 and 5 as you can. Do another one though by just taking 3 squared times 3 times 5 squared. In other words, all the same prime factors, but splitting it up into 3 separate terms as opposed to just 2 terms. Another one we could do, what would be another way we could split up 675 into products of powers of primes like this? Products of powers of primes. Sounds like a good name for a band. Nice alliteration to it. Products of powers of primes, PPP. Okay?
We could just take 3 times 3 times 3 times 5 squared.
3 times 3 times 3 times 5 squared. Could certainly do that. Just split up all of the factors of 3, split up 3 cubed into just individual factors of 3. What's another way we could do it? What?
3 cubed times 5.
Okay. Keep the 3's all together in a single term, but split up the 5 squared into 2 separate factors of 5. I like it. What would be another way we could do this? Yeah, Kelly?
3 squared times 3 times 5 times 5.
3 squared times 3 times 5 times 5. Well, I like this. You all are coming up with the list in the same order I have it in my notes. And then I think there's one more that we need.
3 times 3 times 3 times 5 times 5.
Just all the primes all by themselves. You can have a 3 times 3 times 3 times 5 times 5. So this is going to be all the ways that we can break up 675 and write 675 as a product of prime powers. It's just write it as prime to some power times prime to some power times prime to some power, etc. Just 3 cubed times 5 squared, 3 squared times 3 times 5 squared, 3 times 3 times 3 times 5 squared, 3 cubed times 5 times 5, 3 squared times 3 times 5 times 5, and 3 times 3 times 3 times 5 times 5, it's a tongue twister. 3 times 3 times 3 times 5 times 5. Each of these is going to give us a different way of decomposing an abelian group of order 675 into the direct product of a bunch of copies of Z mod NZ. So the first, the 3 cubed times 5 squared, is going to give us an abelian group of Z mod 27Z plus, or direct product Z mod 25. Or if you want, you could write this as Z mod 3 cubed, direct product Z mod 5 squared. And this would be one way of having an abelian group of order 675. is to just take copy of Z mod 27, a copy of Z mod 25Z, and taking the direct product of those two groups. Second way we could do it is split it up into three terms. One factor of Z mod NZ, where we get a 3 squared, so a Z mod 9. Another factor where we just get a Z mod 3. And then a third factor where we get a Z mod 5 squared, which will give us a Z mod 25. And so another abelian group of order 675, a distinct one, meaning it's not isomorphic to the one before it, would be take Z mod 9, Z mod 3, Z mod 25, and then smush them all together using a direct product. Would give us another abelian group of order 675. How can we write out our third abelian group using kind of this third factorization in the same way? That way.
Z mod 3, direct product, Z mod 3, direct product, Z mod 3, direct product, 25.
Bingo. That's exactly right. And we can similarly go through with the last three, and we'll get a Z mod 27 plus Z mod 5 plus Z mod 5. We'll get a Z mod 9 plus Z mod 3 plus Z mod 5 plus Z mod 5. And finally, Z mod 3 plus Z mod 3 plus Z mod 3 plus Z mod 5 plus Z mod 5. And boom. There are our 6 abelian groups of order 675. And according to what this theorem tells us, is that any abelian group of order 675 has to be isomorphic to exactly one of these 6 groups. Any abelian group of order 675 must be isomorphic to exactly one of these. And remember, isomorphic to meaning shares all the same properties as, mathematically the same group as. So no matter what group of order 675 you give me, assuming it's abelian, I could tell you, oh, it has to have all properties in common, be basically mathematically the same as one of these 6 groups. Direct products of a bunch of copies of Z mod and Z. Let's stop for a second and see what questions y'all have about this before we play around with a couple example questions. So I've got a question. So Dr. Gerstle, you say that all groups of order 675 have to be isomorphic to one of these things. Well, what about the cyclic group, Z mod 675? Shouldn't that be isomorphic to one of these things? You are absolutely correct. Good question, Dr. Gerstle. Z mod 675 should be isomorphic to one of these 6 groups. Because Z mod 675 is an abelian group of order 675. Therefore, according to the fundamental theorem, according to good old gag, it has to be isomorphic to exactly one of these 6 things. Which one? I'll give you a hint. I don't want to write this hint out. I'll give you a hint. Check out the last theorem. Check out the last corollary on the previous page. Last corollary says Z mod 675Z is going to be isomorphic to a direct product of a bunch of Z mod KZs, where the K's all multiply to give you 675, if and only if the GCD of all of the terms of all of the K's, so like 27 and 25, 9, 3, 25, 3, 3, 3, 25, GCD of all of the individual factors comes out to 1. So I claim that only happens with one of the 6 groups in our list. Which one of the groups in our list has the GCD of all of the terms comes out to 1 if you put them in pairs? All right.
The last one.
The last one? So you're saying the GCD of 3 and 3, 3 and 3, 3 and 5, 3 and 5,
Or no.
5 and 5, etc. all comes out to 1?
Just kidding.
You say, yeah, because GCD of 3 and 3, for instance, would not be 1, so I don't think it's the last one. I think you're thinking along the right track, though. Right?
Is it the first one?
Only 2 terms we have to check in the first one. Are 27 and 25 relatively prime? I think so. I think I agree with you. I think this one is actually going to be the one that's isomorphic to Z mod 675. In other words, this one is going to be the only one of the 6 groups in our list that turns out to be cyclic. So you can say Z mod 675 is isomorphic to Z mod 27 and plus Z mod 25, since the GCD of 27 and 25 is equal to 1. Any of these other 5, you're going to be able to find 2 terms where the GCD is something other than 1. So for the second one, for instance, GCD of 9 and 3 is 3, not 1. The third one, let's take these 2 copies of Z mod 3. GCD of these 2 terms will be 3, not 1. Any of the last 3, you can always just take Z5, 5. GCD of 5 and 5 is 5 and not 1. So for any of these last 5, you can always find a pair of terms whose GCD is something other than 1. But only in this first one in the list can you get just 2 terms where 27, 25, those do have a GCD of 1. So according to the corollary on the last page, we know that has to be the one that Z mod 675 Z is going to be isomorphic to. How about this one? You can write 675 as being 45 times 15. So which one of these is going to be isomorphic to Z mod 45Z, direct product Z mod 15Z? That's an abelian group whose order is 675. So 45 times 15 is 675. So we should be able to find one of these 6 groups and be able to say Z mod 45 plus Z mod 15Z is going to be isomorphic to. This one's a bit tricky. And here, it might help to just write out 45 and 15 as products of primes. Let's see, 45 is going to be equal to what? 3 squared times 5. 15 is going to be equal to just 3 times 5. So we would like to have a group where we have 4 individual terms, one with a 3 squared term, one with a 5 term, one with a 3 term, and one with another 5 term. So which of these 6 groups is going to have 4 terms corresponding to 1 for 3 squared, 1 for 3, 1 for 5, and another 1 for 5? Right?
The fifth one.
9355, 9355, if you're onto something. It's going to turn out to be the case that Z mod 45, direct product Z mod 15, is in fact going to be isomorphic to the fifth one. The Z mod 9, the Z mod 3, Z mod 3, or sorry, Z mod 5, and then a Z mod 5. And the reasoning is, if you split apart Z mod 45, we know this, Z mod 45 is going to be isomorphic to a Z mod 9, direct product of Z mod 5. That's because the GCD of 9 and 5 is 1. So we can use that corollary on the last page to say Z mod 45 should be isomorphic to a copy of Z mod 9 and Z mod 5. Z mod 15 should be isomorphic to a copy of Z mod 3 and a Z mod 5. Because 3 and 5 are relatively prime, so their direct product should be isomorphic to Z mod 15. And so then, since the direct product of these two things is going to be isomorphic to a copy of 9, 5, 3, and 5, the only one of the 6 groups in our list that'll be isomorphic to something involving all 4 of these terms would in fact be this fifth one here. And I want to do one more. Let's do one more. This is an example. Which is going to be isomorphic to Z mod 225 plus a Z mod 3. Well, 225, because 225 times 3 is 675, so this should be an abelian group of order 675. 225, we can write as being equal to, what, we need everything but a 3, so 3 squared times 5 squared. This thing is, well, just 3. So we need a group in our list that has a 3 squared term, a 5 squared term, and a 3 term. Which one of the 6 groups in our list is going to have a 3 squared term, a 5 squared term, and a 3? Second one. Bingo. So number 2 is going to turn out to be the case that Z mod 225 direct product Z mod 3 is going to be isomorphic to Z9 direct product Z mod 3 direct product Z mod 25. And so if you're ever given some abelian group and you want to say which one of the 6 groups in this list is our thing going to be isomorphic to, you just kind of have to piece out how can we write each of these terms as a product of primes. So 225 is 3 squared times 5 squared. 3 is, 3. And then just find which of the groups in your list has a 3 squared term, a 5 squared term, and a 3 term. Or which of the groups in our list has a 3 squared term, a 5 term, a 3 term, and a 5 term. And then you just kind of got to follow your nose. And fundamental theorem will tell you any abelian group of that order should be exactly one place in that list. Questions or comments about what we did? Awesome. Turn the page and do it yourself now. I want you to classify all abelian groups of order 80 for me. And not only do I want you to classify all abelian groups of order 80, spoiler alert, there are 5 of them. I want you to also tell me if the 3 groups at the bottom of the page, which one of the groups in your list of 5 are each of the ones at the bottom of the page going to be isomorphic to. So go ahead, take a few minutes and think about this. If you want, you can talk to your neighbors, but be careful. And we'll come back together as a class in a few minutes and talk this one through. There's my hint. See if you can replicate the same procedure that we did on the last one. And to start with, it might be helpful to try and write see how many ways is it there possible to break up 2 to the 4th into the product of some copies of 2. And as always, for those of you watching the video, I encourage you to try this out for yourself at home. You can get mileage out of this. Nice list. There's a sneaky one in here. That is the sneaky one.
It did sneak the first time I got them out.
Well, that's why you gotta be more vigilant. Don't let it sneak up on you.
Yes, sir.
So always feel free to flag me down if you have any questions or feel like you're not quite sure how to get started. We can't have that. Let's give it about 1 more minute and then we'll come back together as a class and talk about these. Do you feel like you figured it out? In the meantime, in your notes, draw a picture of a rubber band.
What?
I'll give you something to do. Completely different order. But I think it's, I think I do know.
Yeah, I just won't do that.
So that's just. All right, let's come back together. Who has the favorite factorization of 80 that they would like to start with? Hmm?
2 squared, and 5.
Oh gosh, you're starting with one of the middle ones. Okay, 2 squared, 5.
Consider it
I like it. That's the tricky one. 2 squared times 2 squared is a perfectly valid way of factoring 2 to the 4. What would be another way? Valerie?
16 times 5.
16 times 5. 2 to the 4th times 5. That's the one I wanted to start with. To be fair, the order in which you write them down does not matter at all. I'm just trying. I like to put kind of the highest powers first in my listing and kind of work my way down to the last one being the one where it's just all single factors. But that's more personal preference. There's nothing wrong with. So as long as you've got them all, the order in which you have them doesn't really matter. It's another one. Right? 2 to the 3rd times 2 times 5. I like it. Sure, give myself enough room here. Okay. I need raising your hand several times. Give me one.
2 squared times 2 times 2 times 5.
2 squared times 2 times 2 times 5?
Yeah.
Awesome possum. What's the last one?
2 times 2 times 2 times 2 times 5.
2, 2, 2, 2, 5. I like it. And then, if we break them all up, our first one will just give us a z mod 16 plus z mod 5. Second one will give us a z mod 8 plus z mod 2 plus z mod 5. Third one will give us a z4, another z4, and a z mod 5. Fourth one will give us a z mod 4, a z mod 2, a z mod 2, and a z mod 5. And the last one, Dr. Gerstle, why do you give ones with so many prime factors? You're going to cramp your hand up writing these all down at the board. It's going to give us one with 4 copies of z mod 2, excuse me. And a z mod 5. If by chance you happen to put the 5 first before all the 2 terms and had, say, z mod 5 plus z mod 16 or z5, z2, z8.
That's terrible.
Lauren disapproves of it, but I am perfectly okay with it. And since I'm the professor in this class, it's my opinion that matters. So, turns out the order of the terms within each factorization doesn't really matter. There'll be, this thing, for instance, will be isomorphic in turn to Z mod 5 plus Z mod 16. Technically, they're not the same group, but they are isomorphic. So the order of the terms within each of these decompositions doesn't really matter. It's just what matters is which individual terms you have. So one with a 16, one with a 5, one with an 8, 2, 5, etc. All right. So, which of these is going to be isomorphic to Z mod 80?
Z mod 5, direct product,
This first one?
yeah.
So I had to make that comment earlier because I saw that you all had put them in the opposite order from what I did, which is perfectly fine. And I agree. It's going to be isomorphic to Z mod 16 plus Z mod 5. Why that one, Seth?
Why now?
Yeah.
The same way we did that one.
Imagine that. What makes it the same? And don't say because it's the first one on the list.
I don't know, they're not all little factors.
All right, well, I mean, it follows the same pattern as the last one, but what made the last one? What made Z675 isomorphic to the Z mod 27 plus Z mod 25? Someone want to help her out? Right?
16 and 5 are relatively prime.
Yeah. I would say here that comes since the GCD of 16 and 5 is equal to 1. Whereas with these other four groups, you can find individual groups in the decomposition who have GCDs not equal to 1. So in the second one, 8 and 2 don't have a GCD of 1, 4 and 4 don't, 4 and 2 don't, 2 and 2. You can always find pairs of groups and you can always find pairs of summands in 2 through 5 where the GCD is something other than 1. But in this first group, 16 and 5 are relatively prime. So that is going to be the cyclic one of the bunch. How about 20? So how about Z mod 20 plus Z mod 4? Each of these 5 groups is going to be isomorphic to that. Yes, Elaine.
I did Z mod 4, direct product, Z mod 4, direct product, Z mod 5.
So the middle one?
Yes.
Why?
Because 20 is, Z mod 20 is isomorphic to Z mod 4, direct product, Z mod 5. Since 4 and 5 are relatively prime and multiply to 20, and then Z mod 4 is just to itself.
Yeah, I agree. Z20 is isomorphic to Z mod 4 plus Z mod 5 because 4 and 5 are relatively prime. Z4 is just Z4. And if we have a Z4, a Z4, and a Z5, that's going to give us this third one in the list. I concur. Finally, how about this last one? 10 for 2. Can't read my own handwriting.
I said it's equal, or isomorphic to the fourth one.
4225. Why is that?
Because it would be like 10 is 5 times 2, and then 4, and then 2.
Yeah, so this term is going to be isomorphic to a Z mod 5 plus a Z mod 2, since 5 and 2 are relatively prime. 4 and 2 are okay by themselves, so if we have a 5, 2, 4, 2, that's going to give us the same terms as the fourth one. This will be isomorphic to Z mod 4, Z mod 2, Z mod 2, and Z mod 5. Yeah, this is kind of the basic procedure for classifying all abelian groups of some fixed order. You start by just looking at how can we factor, say, 80 as product of powers of primes, the PPP, so 2 to the 4th times 5, 2 cubed times 2 times 5, etc. You get a bunch of copies of Z mod NZ out of the deal. Yeah. And then finally, If you want, you can go through some groups and try and see, hey, I have a group in mind of order 80 that's not on this list. Well, it is going to be isomorphic to one of the things on this list, and then you just kind of got to break apart each term like this to find out which thing in the list your group is isomorphic to. Any questions? So I did check this out, and yeah, the proof of this would probably take us about 4 or 5 pages in the packet. So I'm going to skip it for now. The non-abelian group version was indeed, I looked it up, close to 20,000 pages. The proof, proven over many decades. Hundreds of mathematicians took part, and turns out was the longest. Is the longest ever mathematical proof. Fun fact. The problem of how can you classify how can you come up with a classification theorem for non-abelian groups?
So what is like the use of this that got people to spend all of this time writing this proof?
Because it's fun. It was more just people wanted to. There wasn't really a practical use so much that people had in mind for like, why did people want to do this? It was more just there are a lot of mathematicians out there that like, it'd be really nice if we could have a procedure of just saying, oh, you want all groups of order 80? Here, it's one of these things. Just to give you a sense of what kind of groups are in there. The kind of basically the way of saying non-abelian group has to be isomorphic to one of these things involves something called semi-direct products, which is harder than direct products, and we're not going to get into those in this class. Because they're scary. It also involves using groups that just include Z mod NZ, copies of Z mod NZ, the alternating groups, a special type of group called Lie groups, and is it 24 or 26? I forget. Like 20-something special groups called sporadic groups, including a really big group called the monster group. There's a thing called the monster group. And it is big and scary, as the name suggests. But we're not going to go through that theorem because it's way too messy. I'd have to spend the rest of the semester explaining what things mean. Oh, and Lie groups. I forgot the Lie groups, which are a special type of group. Lie spelled L-I-E, named after a mathematician who did a lot of work in algebraic geometry. All right, one more theorem, though, for us in our packet, and that's the converse to Lagrange's theorem for abelian groups. So you remember how we said, in general, given let's say you have a group of order n, if k divides the order of n, if your group is a cyclic group, then you have to have a subgroup of order k. If your group is non-cyclic, then you don't necessarily have to have a subgroup of order k. For instance, we said that 8 divides the order of A5, the alternating group on 5 elements. But A5 has no subgroup of order 8. It turns out that if you have an abelian group does have to have a subgroup of every order dividing the order of the group. In other words, the converse to Lagrange's theorem does hold true if you're working with an abelian group. And we can actually use our good friend Skag in order to prove the converse to Lagrange's theorem has to hold true for abelian groups. So let's see if we can write that out. Dr. Ursula, why are you throwing chalk at the ceiling? You're going to damage something. You're going to have to pay for it. This is the Lagrange's theorem converse for a group. And what this says is that if G is a finite abelian group, and K divides the order of G, then G must have a subgroup of order K. This is something that we already proved had to be true for cyclic groups, but we didn't know before today that it had to be true for abelian groups in general. Because this is certainly not always going to be the case, because the A5 example we saw last week, but it is going to work out for abelian groups that if K divides the order of G, G has to have a subgroup of order K. One thing I will point out is that with cyclic groups, we'd have a unique subgroup of each subgroup dividing the order of the group. It's not going to be unique this time. We're going to have something's not quite working out. But there has to be at least one of every. Here's our proof. We're going to suppose G equals some value. We're going to suppose that the order of G is equal to P1 to the alpha 1, P2 to the alpha 2. Why am I using alphas? Let's use R's. P1 to R1, P2 to R2, up through Pn to the Rn. And G is isomorphic to Z mod P1 to the R1, direct sum blah blah blah, Z mod Pn to the Rn. For some primes, P sub I and integers R sub I. So in other words, we're assuming we have a finite abelian group, which if we do, according to the fundamental theorem, according to Gag, G has to be isomorphic to some expression of this form. So we're going to assume that G is isomorphic to something of this form. And then we could say that if K divides the order of G, meaning K divides this lovely product of primes, we can actually say something about what K has to be. K has to be equal to P1 to the Q1, P2 to the Q2, up through Pn to the Qn, for some Q sub I less than or equal to R sub I. So what am I saying? So we're saying if the order of G is this product of primes, and if K divides that, well, the only way to have some number K that divides this product of a bunch of primes is if you have a number K that has the exact same prime factors, but fewer of them. So, for instance, if we had something like 2 cubed times 5 squared, and I wanted to look at factors of that, the only factors of 2 cubed times 5 squared that I can come up with are going to be terms that just have powers of 2 and powers of 5, 5 in them. If I had something with a factor of 3, anything with a factor of 3 isn't going to divide 2 cubed times 5 squared. I would get stuff that looks like, well, 2 cubed times 5 squared itself, but 2 squared times 5 squared, 2 times 5 squared, 2 cubed times 5, 2 squared times 5, 2 times 5, 2, 5, and 1 would be our factors. And if you notice, all of these just have the same prime factors as up here, but just fewer of them. In this case, we could even say 2 times 5 to the 0, 5 times 2 to the 0, 5 to the 0 times 2 to the 0. And so K divides the order of G. K has to be something of this form. We'll continue this on Wednesday. So on Wednesday, we'll finish this proof, and then we're going to move on to the next packet. In the next packet, we're going to talk about what does it mean to take a group and divide by another group. Instead of multiplying them together, we're going to talk about division of groups and get to quotient groups, which is really cool and fun, and involves lots of cosine. If y'all are ready.